G'day! In this video, we're going to be looking at unpacking Lenz's law and Faraday's law to explain the concept of electromagnetic induction. So this video focuses on dot point 6.3.2. We're still looking at what happens to stationary and moving charged particles when they interact with electric and magnetic fields. Essentially, we're looking at induction. And dot point 2 is actually quite extensive. And today we're going to be going through the basics that will allow us to start to analyze Faraday's law and Lenz's law to a bunch of different scenarios and applications. Our learning intentions today are to first define electromotive force and identify some examples, some we're already quite familiar with. We're then going to identify Faraday's law, and from there we'll explore the variables which cause electromotive force, and also start to unpack how they can result in writing up some different variants of the Faraday's law equation, also known as the electromagnetic induction equation. To finish off, we'll look at Lenz's law briefly and start to unpack some of its implications. So first off, the electromotive force. It's a change in energy per unit charge. This should be a familiar definition already. That's joules per coulomb, which is volts essentially. An electromotive force essentially makes current flow by giving charges energy, which allows them to then move in a set direction. So we've already looked at things which cause current to flow, for charges to get energy and to move. Essentially, the electromotive force, which we are already quite familiar with, is potential difference. And this exists between areas of differing electric potential. Generally speaking, that would be a positive and negative terminal of a power source, but there are other examples of electromotive forces which come under the banner of potential difference, one of them being storm clouds on the surface of the Earth, which have two different potentials, and that potential difference leads to charges moving in a set direction based on that electric field. However, the new concept that we're going to be looking at in this inquiry question is all about induced electromotive force or electromagnetic induction. Essentially, what we're talking about here is a change in magnetic flux, which is able to induce an electric field and causes current to flow. When you look at it just as a single sentence, it can become, it is a little bit of an abstract concept. So let's have a look at some more specific examples. So here are two scenarios where electromotive forces can be induced into coils of wire. I can take a magnet and pass it towards and through a coil of wire. And as you pass the magnet through, you're actually going to start generating a current inside the coiled wire. In these examples of electromagnetic induction, again, the electric current is happening because there is a change in magnetic flux. So in this case, for example 1, we're changing flux by changing the size of the magnetic field that is around these wires. So in a scenario where the magnet is outside of the coil, there essentially is no or a negligible amount of magnetic field that is influencing these wires. But as we push the magnet towards and potentially inside the coil, what's going to happen is that the magnetic field that is near those wires is going to increase. So because we've gone from pretty much no magnetic field to a higher magnetic field, the flux will increase. And because the flux has changed, the flux has increased, that is going to lead to a current being induced inside the wires. A similar effect can happen when you have a magnetic field that is consistently being applied to a wire coil like this one. In this scenario, if you were to turn that wire coil, you would also be getting a change in flux because, as we talked about in the previous video, you can increase and decrease flux by changing the angle which is between the magnetic field and the normal to the area of the coil. So if you've got the coil rotating around and around and around, there'll be periods of maximum flux, periods of minimum flux, and everything in between. So as it continues to turn, you're going to be getting more and more electromagnetic induction, meaning that there is going to be a current that's running through this coil, which can be used to power some sort of electrical appliance. This base concept is actually how most electricity in Australia is generated. So how can we take this concept and start to analyze it in a more quantitative manner? Well, here we have Faraday's law. We have that epsilon is equal to negative n times the change in phi over the change in t. So lowercase epsilon here is the electromotive force. And that's what's being induced by a changing magnetic field. The electromotive force is measured in Tesla meter square per second, or that is just another way of putting down volts. So this is a voltage, that electromotive force, which is causing a current. The electromotive force and the size of it is going to be dependent on a couple of things. The first one here is N, which is the number of coils of wire. Essentially, if you have more coils in the wire, which are able to all experience an electromotive force and get an induced current, essentially the amount of EMF generated is additive. So more coils means more electromotive force. The other variable in this equation is the change that's happening in the magnetic flux. And we know that magnetic flux is determined by the amount of magnetic field that's there, multiplied by the area of the coil of wire. And we may need to involve theta in that calculation depending on what the angle is between the magnetic field and the normal to the area of the coil. Lastly, we need to know how much time is occurring as this magnetic flux is changing. So that's why I've got delta T on the bottom there. So again, as has already been highlighted in this video, the electromotive force, which is going to generate a current in a coil, is only going to happen if there is a change in magnetic flux, where magnetic flux is increasing or decreasing. In the video previous, we talked about a few methods to change magnetic flux, and that is based on the variables in the second equation down here. Those three variables being the amount of magnetic field that the coil is experiencing, the area of the coil, or the angle between the magnetic field and the coil. Area is generally hard to change. The coil is usually fixed in shape. So we're mostly worried about either increasing or decreasing the magnetic field strength or changing the angle between the coil and the magnetic field. And depending on what kind of apparatus we are focused on, will dictate as to which of those two variables is actually changing in a given scenario. In general, though, we can write the Faraday's law formula to include some of those variables. However, because one of these variables is generally changing at a time in order to get the magnetic flux to change, we can rewrite this equation to make it a little bit more simpler and straightforward. Now, the first variant of the equation accounts for a change in magnetic field strength, and the second variant of the equation accounts for a change in the angle between the magnetic field and the normal to the area of the coil. So something that you may have noted while looking at some of these equations is that when we have Faraday's law, we can see that the EMF is always negative. And this is due to Lenz's law, which is a little bit more of a conceptual law in a way. Essentially, Lenz's law is applying the law of conservation of energy to electromagnetic induction. And again, we can see that for the negative symbol on the electromagnetic induction formula. What Lenz's law states is that the direction of the electric current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes changes in the initial magnetic field. In other words, if I were to push a magnet towards a current carrier and induce electric current into that current carrier, in this case, we've got a loop, the direction of the current could either go, in this case, up or down, clockwise or anti-clockwise. However, it will only go in one direction, and that direction will essentially produce a magnetic field which pushes back against the magnet. It's a resisting force. So in the first diagram, we see here that the magnetic field is pointing to the right. Therefore, the magnetic field, which is going to be generated by the induced current, is going to point towards the left. Therefore, what that means is if we want magnetic field pointing towards the left, then the current needs to be pointing up, or I guess anti-clockwise in this diagram. And so if you use your right-hand grip rule, you will find that if you've got that current pointing up on the closest side of the ring, that is going to generate a magnetic field, which does loop around and point back towards the left. And this opposing magnetic field is really important to the law of conservation of energy because If the current were to go in the other direction and the magnetic field that was generated by the induced current went in the opposite direction, it went from left to right, essentially you would be generating a magnetic field which would only be supporting the original motion and would actually help to pull the magnet through. Realistically, in our world of physics, that concept does not work. That is impossible because you would actually be generating energy from nothing. Effectively, if that were the case, that would be the means to be able to create a perpetual motion machine, which is impossible to make. The energy needs to be coming from somewhere. Now, as we dive deeper into the rest of this topic, we're going to be focusing on Lenz's law and Faraday's law pretty much all of the time as we begin to unpack some real life applications of this really fundamental physics. The first thing that we're going to be looking at is transformers, and that will be the topic of our next video. Until then, have a good one.